After completing my Arduino project series, I learned microcontroller programming, fundamental electrical concepts, and interfacing with various sensors and actuators. I was ready to apply these skills to a more complex robotic system, building on the sensor integration, motor control, and programming techniques I developed through my experiments. Up to this point, I had already worked with ultrasonic sensors, servo motors, IR communication, and motor drivers. So with these experiences, I built my first complete robot, a dual-mode robotic RC car. This project basically synthesized everything I had learned into a practical application. This robot car features two distinct operating modes: a manual driving mode controlled via infrared remote for direct human control, and an autonomous obstacle avoidance mode that allowed the robot to navigate independently using sensor feedback and algorithmic decision making. I based this project around this eLego Smart Cart kit, but custom programmed the whole device in 614 lines of code using the Arduino framework in C++, which you can see with this GitHub link in the description. But if you want to buy each individual component for cheaper, the main things you need for this project goes as following: an Arduino Uno R3 board. The Uno R3 board is the main microcontroller that runs my software. It controls all other components. It's the brain of the robot, where all the sensor integration and command signaling takes place. TB6612 motor driver. The TB6612 motor driver amplifies the low power signals from the Arduino to control the high power DC motors. It allows the Arduino to control motor speed and direction without damaging itself. 4 of these motors to drive the wheels and have enough torque to push the robot chassis with all of its components. The HC-SR04 ultrasonic sensor measures distance during autonomous obstacle avoidance by sending out an ultrasonic sound wave and timing how long the sound waves takes to bounce back. This is how my robot sees obstacles. The infrared receiver module receives infrared signals from the remote controller, allowing you to manually drive the robot. The infrared remote is what actually sends the IR signals to the receiver module, which control the robot manually. You can go forward, backward, left, right, adjust the speed, and toggle the autonomous driving mode. One servo motor, which rotates the ultrasonic sensor to certain angles, left and right, so it can scan for obstacles in different directions. A 7.4 volt lithium battery pack with 200 milliamp hours. This powers the entire system, providing enough voltage and current capacity to run the motors and electronics. You also need the appropriate wiring to attach the sensors and actuators to the microcontroller for input and output signaling. On the mechanical side, you just have the robot car chassis, which consists of an upper and a lower plate, a piece to hold in the servo, assorted screws obviously, 4 wheels and mounting brackets and lifts. Also, the original holder for the ultrasonic sensor broke, so I 3D printed this one with the face, just to make it a little more human, I guess. The RC car has 2 modes, a manual mode and an autonomous mode. In manual mode, you have direct control of the robot using an infrared remote control. You can drive it forward, backward, turn left or right, and adjust the speed with dedicated buttons on the remote. This mode gives you precise control over every movement, making it perfect for navigating tight spaces or performing specific maneuvers. The robot instantly responds to your commands through the IR receiver module, which decodes the signals from your remote. Autonomous mode. In autonomous mode, the robot becomes self-driving. It uses servo-mounted HC-SR04 ultrasonic sensor to scan its surroundings by rotating left and right, measuring distance to obstacles in different directions. Based on this sensor data, the robot's algorithm makes real-time decisions about which direction to move, choosing the path with the most clearance, continuously scanning and adapting to avoid obstacles without any human input. You can switch between manual and autonomous modes at any time by pressing the star button on the remote, allowing seamless transition between direct control and independent navigation. The entire system is built in C++ using the Arduino framework, totaling to about 542 lines of code. So at the top, I just import the necessary libraries. For this project, I'm using a library for the IR remote and the servo. This just makes communicating with these devices easier. So this is basically just the pin that each of these sits on. So for the IR remote pin, it's not even the remote, it's really the sensor pin because the remote isn't physically attached to the device. You see the trigger pin, basically just triggers the echo signal, and then the echo pin, which is actually where you read the echo that's sent back. I have some global variables for measuring the distance in inches, the return time. I have a measuring bucket to average, blah, blah, blah. I also have state variables like object detect. This just detects if you're in autonomous mode or if you're not in the autonomous mode. Basically, it keeps state of which mode you're in when you're switching with the remote. These are the pens for the motors. This is like 3 different speed modes. And then you also have the speed for the right and the left. This just communicates like, what pen are you going to be sending the signals to the motor driver, which will control the motors. These are functions that just control the motor speed. So this rates the speed to the left motor. This rates the same speed. These are just the 90-degree turns. These are functions for like basically just controlling the robot and its movement. This switches the motors on and off. This is checking if the right and the left and like which orientation the motors are in. These are all functions to control the motor speed. And then this is to actually send the trigger signal. This is to read the distance. Takes like an average, blah, blah, blah. This is what I devised for the sensor to give me the measurement back in inches. This actually scans the distance. This is where it's taking a scan at multiple angles. You can see the servo position is the angle at which it's taking the scan. And after taking those scans, it picks a winner based off whichever was the shortest distance. And it returns the winner. And that's basically how the automatic turns work. Because then it takes that function of scanning the distance, which returns the winner. And then it drives into whatever space is empty, which correlates to the servo position. Then we have the actual obstacle avoid. This is basically just like the loop that all that runs in, blah, blah, blah. And then it has reading the values of the remote ID to see if you're trying to switch it or not. And then this is the automatic detection. And basically, it drives straight. And this uses distance inch, not the average inch. So the scan winner uses the average of like 20 scans or 10 scans, I believe. But this just uses whatever was the last scan. So while it will drive straight, and then it's using distance inch constantly to take quicker scans instead of doing the averaging. And then based off the last scan, if it's high, if it meets the threshold, which is different for each speed because you're coming at it faster, so you need to stop sooner, it basically will take a deeper scan and do the averaging, where it takes an average of multiple scans at each position for the automatic turns. But while it's just going straight, it's just using the last scan to make it more responsive, because if it's always taking an average, then there could be a scenario where it's taking the average while it's still moving forward and runs into an object. So it just uses the last scan. Now this is the remote control. So basically from the IR receiver, you basically get it back as a hex code. So you just can take each button in their respective hex code and then write a function to that, like the OK button basically turns it on and off. You have the forward button, blah, blah, blah. And then you see, the start button, it calls the echo obstacle avoid, blah, 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 which is this function right here. But inside this function, there's so many functions. There's the automatic turning, there's the taking the scans, blah, 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 blah. But you see, it all is very modular. It's all super organized. I think this is when I actually started making more organized code, because it's very easy for me to just sit down and explain, even though I wrote this code so long ago. Like I wrote this code 2 years ago. And then drive left, drive right, drive backward, speed up, and you see it just correlates to the button. And then this is like the final thing where it just processes the signal, and then it runs each function on the respective buttons. And it also prints out the signal that you got back from the IR receiver. And this is like the setup code. It basically just tells, if the pins are inputs or outputs, like the motor pins are going to be outputs, blah, blah, blah. The echo pin is going to be an input, because that's like reading the trigger of the echo that you sent. The IR pin, blah, blah, blah. But that's handled by the library. Same with the servo. And then in the loop, this is literally where everything runs. So you have the remote sensor loop, so it just constantly checks for remote, and then the button commands, which have the functions nested that I wrote up top for controlling the motors, switching the modes and everything, and going into autonomous mode. So yeah, that's the code architecture. That's it. Some key challenges of this project were balancing manual and autonomous control modes, optimizing the scan algorithms to decide when to use the averages versus just the last scan to reduce latency while maintaining accuracy. Using someone else's PCB design was actually a big challenge that I had with this project, simply because I had never done that before when working with microcontrollers. During my Arduino series of projects, every project I knew the circuit design and I designed the circuit, but with this project it was from a kit that wasn't really meant to be programmed how I programmed it, so I had to go and look at the circuit in order to write my own program. Without knowing the PCB design, you can't effectively program the motors and all the sensors and actuators, because that's how it's wired to the Arduino. Some skills demonstrated were embedded C++ on Arduino with multiple sensors and actuators, real-time state management and event-driven programming, algorithmic decision-making for autonomous navigation, hardware-software integration, and optimization of limited computational resources, just due to the Arduino being a microcontroller, very limited in its computational power. Debugging and optimization using serial communication protocols, like basically debugging through the serial monitor. Signal processing and noise filtering for reliable sensor reading. Modular code architecture, as well as timing and synchronization management for coordinated robotic movement. The challenges I overcame during this project deepened my understanding of mechatronic system design. This project gave me a solid foundation in embedded systems programming and prepared me to take the next step, exploring ESP32 microcontrollers for their extra power and to add IoT capabilities or Internet of Things to future robotics projects, fusing my skills that I developed in web development and robotics.